All right, welcome back to Trig. 5.2. Oh, this is where it gets fun. This is the trigonometric form of complex numbers. What? Complex numbers? With trigonometry, how does that work? Well, I'm going to show you here. Let's take a quick look. All right, so here's the notes. We're going to go through some problems here in just a few minutes. But I do want to walk through this with you because I think there is really a lot of good content in this particular section. I'm not usually very proud of the notes that I write up, but I really, man, these are some real good notes. I'm just going to tell you right now. I don't normally toot my own horn, but toot toot, here we go. All right, so for real numbers in two dimensions, we use what we call the Cartesian coordinate system. It's on an XY plane. Complex numbers, we graph them on what's called the complex plane. So the horizontal axis, which we normally have as the x-axis, we call it the real axis. The vertical axis is the imaginary axis. Now I do want to point something out. Your textbook uses this guy right here, z is equal to a plus bi, or ib. I'm using x and y. Okay, that's just... the reason why is because it becomes completely abundantly clear which component is the x value and which component is the y value. You can actually think of this as like a vector almost. So this is the imaginary axis. We have phi here is the angle that is being created with the argument, which is r, and then the something that you'll see down here below is just the complex conjugate, which is actually, you just take it and you flip it down. So you've got a positive IY, you make it a negative IY. Okay, that's what's called the complex conjugate. It's referenced with a little bar over top of the Z. Sometimes in, like if you're studying statistics, they use the bar to mean something different, but in complex land, I'll call it, we'll be using this to represent the opposite. Okay. All right, so in the image above, we have r is equal to the absolute value of z, and the absolute value of z is just going to be the square root of x squared plus y squared. It's just using the Pythagorean theorem. All right, the trigonometric form. So how do we get the trig form of a complex number? If you have z is equal to x plus iy, it can be rewritten as z is equal to r, which is the length of this guy, times the cosine of the phi right there, plus I sine phi. And here's why this works. Remember with the unit circle how we said that if you have an xy coordinate in the unit circle, the cosine is going to equal the x value and the sine is equal to the y value. Well, this is why it works here, because the x value is just going to be the cosine of this, and the y value is just going to be the sine of that times I. So it's pretty cool. So there's a way that we represent this in math. It's called the cis. So r cis phi is just taking this whole. So the cis part is just the cosine phi plus I sine phi. Here you have the cosine, the I, and the sine. So that's just the way that we represent it. And then I've got those defined here. X is equal to r cosine phi. Y is equal to sine phi. I think I made a mistake there. I'm missing something. Let me just go back and double check. I think I'm missing an R. Yeah, I am. There should be an R there. R sine phi. Hey, how about that? And then R is equal to the square root of x squared plus y squared. And I did not include the second part of that, so I'll have to fix that. Tangent, it should be tangent of phi is equal to y over x, not tangent y over x. It's tangent of phi. I was so proud of my notes and tooting my own horn. Now I have to go back and fix them. Ugh, guys, not good. All right, so the product and quotient of complex numbers. So here is, I worked it all out for you. I don't normally put proofs in here, but I just thought this one was interesting. So if you have two numbers, z1 and z2, they're written in trigonometric form, you can actually go through it and use some of the identities that we've worked on in the past to get down to something that's kind of interesting. So z1 is equal to r1 cosine phi1 plus I sine phi1. z2 is r2 times cosine phi2 plus I sine phi2. When we multiply them together, we get this. We can move some things around. We'll get an I squared when we multiply out the two factors. So when we multiply this factor here in the end and this factor here in the end, what we'll end up doing is the I sines for both of those are going to multiply, and we get an I squared. Well, the cool thing is I squared is equal to -1. So now we're going to take this piece and bring it to the back, or I should say up to the front, combine these together and combine these together, and these are actually just using some of the sum identities to get these pieces. So we have cosine phi1 plus phi2, I sine phi1 plus phi2, so that actually equals r1 r2 cis phi1 plus phi2. Okay? So it's a cool little proof in here just using some of the identities that we've worked on. That's kind of why I wanted to include it. Now, I did not do the quotient property. It's pretty much identical. There's just a few things that just get moved around. But in the end, what you get is z1 over z2 is equal to r1 over r2 times cis phi1 minus phi2. Now, here is the thing. This is a minus. The cool thing is that this minus sign mirrors some of the properties of exponents. And actually, that, I'm kind of shocked that they don't bring this up in this class, and I may talk about it at some point here in the next week because we're almost done. But there's actually a way to represent this all in the imaginary land of the complex coordinate system using exponents. In fact, let me switch to my whiteboard because I want to show you something that is kind of bananas. Let me turn my focus ring off. Give me just a second here. Check this out. So what we have is that if you have e to the I times phi, that just looks like a 4. I'm just going to use theta because it's easier to draw. I should have used theta in the notes, but, whatever. This is equal to cosine theta plus I sine theta, which is pretty bananas when you think about that. We're not even going to talk about this, which I think is kind of crazy in a trig class that this isn't going to come up, but it's awesome. This is pretty cool. So what's a direct result of this is that if you have e to the I pi, this is going to equal a -1. This will all work out to be a -1 because the 0 goes away and then you get a -1 here. But check this out. You go do this. You move the -1 to the other side. Okay, I don't know about you, but that is kind of insane. You have e, which is an irrational number. You have I, which is an imaginary number. You have pi, which is another irrational number. Then you have 1, and you also have 0. These are some of the most important numbers in all of math, and they're all in one equation. So this is considered by most people to be the most beautiful math equation ever. So it's kind of insane how it works, but yeah, there you go. That's a little side note for you right there. Again, it's just a different way of representing it. Maybe when we get into polar coordinates, we'll start using some of that. All right, so I want to go through some problems here. We're going to do question number 10. So let me pull the textbook up here. I got it down below me. All right, question number 10 is saying, write each complex number in trigonometric form. Oh, that's not too bad. All right, so 10, we've got z is equal to minus 4 minus 4i. Okay. The x and y are negative, so we're in quad 3. Okay. So the modulus is r, and the argument is phi. I think I actually said the argument was r earlier. The argument is like the rotation, the modulus is the length. So we need to first find what r is equal to. So r is going to equal the square root of x squared plus y squared, which is equal to the square root of minus 4 squared plus minus 4 squared. So that's equal to the square root of 32, and that's going to equal 4 root 2. All right, so let's see here. So that's our r. Now let's just draw this out so you can kind of see how this looks. So here's the imaginary axis, here's my real axis. Okay. So it's going to be something that's out here. This is going to be z equals minus 4 minus 4i. And the angle that we are looking at, which is our phi, is going to be this guy right here, all the way around. So this is phi. And what we need is the reference angle, and I'll just call it alpha. Okay. Now in the textbook they talk a little bit about this. To find the reference angle, it's actually the inverse tangent function. You have to use the inverse tangent. So for the reference angle, what you get is alpha is equal to the inverse tangent of y over x, which is equal to the inverse tangent of minus 4 over minus 4. So that's equal to the inverse tangent of 1, and that is going to equal, if you go back to your unit circle, you can find that, or you can just punch that into a calculator and you're going to get 45 degrees. The calculator method works in this case because 1 is a very easy number to work with. All right, so we've got 45 degrees. So the reference angle is going to be this. We've got phi is equal to 180 plus 45 degrees, which is equal to 225. Okay? So we're not quite done yet. We still got to put it in trig form. And I'm running out of a lot of space here, so what we need is this guy there, that guy there, and that's pretty much it, just the sine and the cosine, okay? So commit those to memory, take a snapshot, pause, boom, and I'll go ahead and write those down for you so you can see. All right, so we got all those pieces, and now what we're going to do is look at z. This is going to equal 4 times the root 2, this is our r, times cis, 225 degrees. So that was our solution to that particular problem. Okay. Question 24. Let's go ahead and take a look here. What does the book say? Write each complex number in standard form. Okay. So pretty much we were going from standard form to trigonometric form. Now we're going back to standard form. So this is going to be z equals 5 times cosine of 120 degrees plus I sine of 120 degrees. Okay? Alright, so now what we need to do is... Hang on, I'm pulling something up. Can you guess what I'm pulling up? Any thoughts, any guesses in your mind? What's the one thing I always say transcends every topic? Oh my gosh, there it is, the unit circle. It's amazing. Okay, so we've got cosine of 120. So let's take a look. 5 cosine of 120 is going to be the x value, so this is going to be a minus 1/2. Okay. And then the sine of 120 is the y value, so that's just going to be plus I times root 3 over 2. Okay? And I just wrote that down, so there you have it. How about that? That is amazing. So now we're going to multiply this all out. This is going to be a minus 5/2 plus 5 root 3 over 2 times I, and there is our final form. So it's really, again, this is just using the unit circle. Gotta love that unit circle. It's pretty amazing. Who knows how well you would do in this class if you did not have the unit circle. I know it would not be that great, because it's amazing. All right, question 28. This is actually going to be the last question. We're only going to have like 5 homework questions tonight, and I'll probably ask you a quiz, give you a quiz here in the next few days, so just bear that in mind. 28. Z is equal to 5 cis 90 degrees. So this is the same thing as 5 times cosine. What's the deal with them using 5 as a modulus every time? I don't get it. Plus I sine of 90 degrees. Okay, cosine of 90, that is going to be a 0. So we've got 5 times 0. Sine of 90 is going to be 1, so that means we've got just I. So this is equal to just 5I. And that is completely sufficient in standard form. You can leave it like that. That's perfectly fine. All right, well, that's what we got today. Like I said, I'll go ahead and post the homework questions here in just a couple minutes, and I will hopefully see you all very soon.